Testing, 1, 2, 3, good. Okay, the third lecture, or the second lecture after the introduction, will consist of an exploration of Greek mathematics. So go ahead and click on the Greek link to Greek mathematics there. And make it any size you need to. Okay, the origin of the Greek civilization, of course, they're in the Eastern Mediterranean, dates back from about 10,000 BC to 3000 BC. Of that period of time, the Stone Age, there's really nothing but just traces of settlements and tribal units. Greek civilization really begins thereafter, 3000 BC. The Minoan civilization, which arose on the island of Crete, dates back to about 2600 BC, and the Mycenaean civilization developed on the mainland about 1600 BC. There was a dark age of Greek civilization going from 1100 to 800. Afterwards, there was a huge flourishing. The Dark Ages resulted from, I believe it's the Dorian invaders. These were an Iron Age culture colliding with the Greek culture, and basically there was this catastrophic disruption of the civilization. They rebuilt themselves shortly after 800 BC. Now we can go and identify some of the very famous Greek philosophers and mathematicians in this list, and we'll talk about them in just a second. I might mention that the Greek history falls into the Archaic period from 660 to 480 BC, the early classical, the Golden Age, the late classical, and then the Hellenistic. The Hellenistic dates from Alexander the Great on through Alexandria in Egypt. So I've got just a few links to just some of the, I'd say, top 10 or so of Greek philosophy and mathematics. There's a very nice reference here to all these below, and this is an index of bibliography. So if you go, let's see, that's maybe not the best one here. For example, Thales, I should mention that in 775, up to that point, the Greeks had been using a hieroglyphic similar to the Egyptian, where an entire symbol would be an entire concept, a word, a series of words. It was not phonetic at all. In about 775 BCE, about 100 years or 200 years before Thales, they essentially borrowed the Phoenician alphabet, and which was the same one that the early Hebrew people had and the Canaanite people at that time. Now, very little is recorded from this period because they wrote in papyrus, unlike the Mesopotamian Babylonian civilization where they did it on clay tablets and fired them and preserved them for a long time. They wrote in papyrus, an early version of paper, so the early writings are not really preserved. We only know about the early Greek works through Arabic translations and other translations about 800 years later, afterwards. So there's a nice sort of article on how does one know about Greek alphabet, or Greek mathematics rather. So you can go through here. The primary problem is we don't have any of the original works. All we have are the somewhat edited, even Euclid's Elements exists only in an edited form. And the earliest manuscript dates back from about 800 AD. So you can go through there, and that's a little bit of a historical aside. Now, Thales is the first person that we'll discuss. He was the founder of the first Greek school, which is called the Ionian School. He was born 624 BC, died 537 BC. If you click on the link, you can read about Thales. And quotes of him, there's actually a Greek historian, Greek philosopher, Proclus, who lived around 450 AD, 1,000 years later. They were interested, even in those times, of doing history of mathematics and history of science, so they were interested in the origin of the Greek civilization 1,000 years earlier. Okay. So he is probably the first major light in the Greek civilization. He had several students, Anaximander and Anaximenes. The most famous of his pupils was Pythagoras. Pythagoras lived from 569 BC to 475 BC, so that's about 80 years, which is quite a long time to live in those days. He, as it says here, is described as the first pure mathematician. He was very interested in geometry, and he founded a school in Greece called the Pythagorean School. Anaxagoras was also one of the philosophers of this day. It's very difficult to distinguish between philosophers and mathematicians in the early Greek civilization, since they're essentially the same thing. And as we'll see, the questions that mathematicians or mathematics raised at that time were essentially philosophical. Zeno is a good example of this. He was a member of another competing school at Arius, which is the Ariatic school. He was a philosopher, and he is probably best known for Zeno's paradoxes, which there was about 40 of them, and we'll get the chance to see one of them. I have it prepared on the web. Democritus, Plato, Aristotle, Euclid, Archimedes, all of these are names that are well known. And I've written them down in somewhat chronological order, going from Thales in 625 BC down to Archimedes in 212. Now, as was mentioned before, Greek mathematics was very heavily influenced by Greek philosophy. Now, it's not clear where the Greeks got their love of philosophy, because before Thales, 200 years before that, they didn't have an alphabet. They were just recovering from essentially the Dark Ages. So where and how did this tremendous love of abstract thought and philosophy come from? It's not really well known, because this philosophical thought heavily influenced their mathematical questions. For example, to the Pythagorean school, all numbers were essentially whole numbers, 1, 2, 3, etc., or they were rational numbers, ratios of whole numbers. They did not know early on in their history of their school that there were, in fact, irrational numbers. I'd say a couple, 30, 40 years after they were begun as a school, someone in that area, I don't have a reference right now, gave the first proof that the square root of 2 is irrational. The Greeks had that proof available to them. It was a rigorous proof that square root of 2 was not a ratio of 2 whole numbers. This really disturbed them. In fact, there's an apocryphal story that the person that discovered it was on a ship with Pythagoreans, and they all threw him overboard. Whether that's true or not, I don't know. The Greeks were also, and this is amazing, they were very concerned with the dichotomy or differences between discrete and continuous. There were huge debates as to whether space and time were continuous or discrete. I mean, these are fairly advanced topics for that period of time in our history. Now, Zeno, who is not in the Pythagorean school directly, but left to become a member of the Ariatic school later on, he formulated the following paradox, in part to answer or to resolve the question, is space and time discrete or continuous? So I have a link to his paradox, and the paradox is the following, and we can discuss sort of what's wrong with this or what the mathematical content or philosophical problems are with this. So he postulated 3 things, and his italic words are his, and my comments are on the side. It says, when an arrow is in a place just its own size, it is at rest. What that means is if you look at an arrow flying through the air, say on a straight line, and if you look at it, say, time 0, and you look at where the position of the back of the arrow is, and then you look at it at some later time, it has gone to an interval in addition to its own length, right? So if it's moving between any 2 successive times, no matter how close together they are, it moves to an interval greater than its own length. So he postulated that when the arrow was in an interval equal to its own length, then it was at rest. And basically everybody said, uh-huh. Now, the second postulate, or the second idea was that at every moment of its flight, the arrow is in a place just its own size. In other words, if you freeze time, in other words, the arrow consists only of an interval equal to its own length. Okay. Therefore, if you put these two together, if an arrow is in a place only its own size, it is at rest, and then at every moment in its flight, it's in an interval equal to its own length, therefore you can conclude rigorously that every moment of its flight, the arrow is at rest. And this was very confusing to the Greeks, right? So roughly speaking, the problem is the following. If you have something moving through the air and you take a snapshot of it at fixed time, they didn't know about snapshots, but if you consider a very small interval of time, the arrow is moving to an interval larger than its own length, okay, between the end and the tip. But if you look at it at every instant in time, it can't stretch while it's moving. It's equal to its own length. So therefore, why at that every instant in time is it not at rest? So another way of phrasing this is velocity equal to a discrete number of intervals at which the arrow is at rest. Or if it's at rest, how does the arrow know how to move? So these were ideas that were very confusing to the Greeks. Actually, it may be confusing to you now, but for different reasons. It's just, some of you may not know what the problem is, because our idea of a limit and continuous and motion and derivatives is so ingrained, but to the Greeks, none of this existed, and they just had a philosophical argument here that said, why is the arrow moving in the air? Because it can never occupy more than its own interval, and if it only occupies its own length interval, it must be at rest, because otherwise it would be stretched. Now, some people have taken apart this and rephrased it. There's another paradox that's sort of related, but following, and I'll give another version of it, and this is called Thomson's lamp paradox. And this is something, again, had the Greeks known about it, they would have loved to discourse endlessly on. So what's wrong with the following argument? You have a lamp that's turned on initially at time 0. And after 1 second, you turn off the lamp. After a half a second, you turn it on. A quarter second, you turn it off, etc. So you just keep alternating back and forth. Now, this does not take an infinite amount of time, right? Because we can sum the series 1 plus a half plus a fourth to be 2 seconds. And in fact, if you sum the intervals, it exactly equals 2 seconds. So the question is, and the paradox is, after 2 seconds, is the lamp on or off? Okay, how many say it's on? How many say it's off? You can't tell, right? It's one of those unanswerable questions. But that bothered the Greeks because they said, why should it be unanswerable? Or had they phrased it this way, it would have bothered the Greeks. But the question is they know the lamp is either off or on, so why can't you deduce the state? And if you can deduce the state, does it make a difference whether the lamp is initially on or off? Another version of this, which is even more contemporary, is picture a photon, a particle of light coming into a series of mirrors at a 45-degree angle. Bounces off the top mirror, then bounces off the bottom, goes to the top, then it bounces off another mirror that's half a distance, goes back to the top, then a quarter, etc. So at the end of this tube with all these mirrors in it, is the photon traveling up at an angle of 45 or down at an angle of 45? It has to be doing something, right? So, does everybody see the problem here? Or is there not a paradox? Now, one of this is not a class in philosophy or theoretical physics or these things, but the Greeks love to formulate questions and then use abstract reasoning processes to answer them. And occasionally they would get a problem which did not seem to be reasonable or does not seem to be able to be reconcilable or resolvable. In this, the fundamental problem is that reality is in some sense discrete. We cannot construct, in fact, a series of mirrors infinitesimally close to one another as you are in the limit. Or you cannot actually turn a switch on and off infinitesimally. Now, this is not an argument for the quantum theory of matter, right? But it is an argument for the fact that you cannot actually perform an experiment that could ever duplicate this. Another example of a paradox, I mean, this is kind of a cute one. It's a later on called the gambler's paradox. So suppose you have a gambling casino and you're developing games for the casino, and you come up with this idea. I say, okay, I'm going to flip a coin. If it comes up heads, I'll pay you $2. But if it comes up tails first and then heads, after 2 tries, you win $4. Or if it comes up tails twice and then heads, you win $8 after 3. So after 4, 16, etc. Now, you all know probably from elementary courses in probability that you can determine whether you want to participate in a game by computing the expected value. Now, if you compute the expected value of this particular game, it's actually infinite. Because what is the expected value? The expected value is the probability of an event times the value of that event. So you get $2 with probability 1/2, $4 with probability 1/4, $8 with probability 1/8. So you see what's happening. The numerator and denominator are the same. So if you sum up an infinite number of these, it's infinite. Now the question is, would you, let me do this down here, would you play a game with a expected value equal to infinity? Well, this sure looks like it, right? There's no risk because you're going to win something, right? Now the question is it costs you to play. This is the rub. Now, what should the casino charge to play? Well, you might say, okay, they could charge $1,000, and over the long run they would lose money, right? Because they're going to pay out. Eventually, one of those times the coin is going to take like 10 tails and then a head, and they're going to pay out a huge amount of money. Okay, so the question is, if it is an expected value of infinity, if they charge $100 or $10,000 to play, and you're a good student of mathematics, and you say, oh, it's expected value of infinity, why wouldn't you pay $10,000 to play this game? Right? Because, I mean, it makes sense, right? If it's expected value infinity, when you play over and over and over again, you're going to win in the long run, right? So what's the problem with, I mean, if I were to ask you, would you pay $10,000 to play this game? No, right? Because, well, the chances are you're going to flip ahead in like 3, and they'll pay you $8, and you paid them $10,000, and you're going to lose a lot of money, right? So here is the paradox, if you will, is somewhat mathematical, but it's more behavioral than mathematical. And in part, the resolution of this is you don't have an infinite supply of money, right? If you had an infinite supply of money, you would pay whatever it takes to play, and in the long run, after millions and billions and trillions of coin flips, you're going to come out in the long run, right? And maybe if you pay $100 million to play after the universe is cold and dark, you might come out, I haven't really done the mathematics of this, like what's the probability of winning more than what you put in on any given occurrence. I mean, you can do things like that. So this is another paradox. It's not a paradox in mathematics, but it's more of a paradox in decision making. And the Greeks really didn't, it's a different style of paradox. We are going to assemble a number of paradoxes in the course. In the book of Boas and Geller, there are some paradoxes in chapter 13, one of which is Russell's paradox of the question, and I'll put this down for next time, is there a set that contains everything? Okay, so suppose there was such a set. If it contained everything, it would have to contain itself. And an element of a set cannot be, in the set itself, so it's a contradiction. So that's one of the facts that there's a Barber's, let me just see if I can restate this in set theory here. It makes a little more sense. The more words you use in these, that can sometimes lead to confusion. So if you define a set, say, suppose you say A is the set of all elements, say, phi, such that phi is not an element of itself. Let me make sure I've got that. So in words, this is a set theoretical paradox, and that's actually the most famous of them. And it comes about in naive set theory, or axiomatic set theory. So for example, it says, call the set of all sets that are not members of themselves S. So S is the set of all sets. So A is a set of all sets. So phi is a set. So that phi is not a member of itself. Now it's not subset, but it's not an element. So then the question is S is S in the set itself or not? So if S is a member of itself, then it cannot be in its set S. So, in other words, is A in A? So, if A is in A, then it does not satisfy the criterion for membership in A. So this says A is not in A. But if A is not in A, then it satisfies the criteria for membership in A. Then you have A is in fact in A. So this is a fundamental problem. You have a set that is essentially too big. So this is like the set that contains everything. There can't be such a set. Because if a set contained everything, then it would contain itself. Now, if you say define this set to be the set phi of all sets that do not contain themselves, what does A belong to? So this is one of those things where you just cannot, it's an unanswerable question, in part because the set A is just too big. Because every set is not a member of itself, so then A is essentially the set of all sets, and that set is too big, essentially, to be a set proper. So a basic paradox is if you assume one thing and then it proves the opposite, when you assume the opposite and it proves what you presuppose, or the criteria for definition, membership, then there's a contradiction. So clearly, if A is not an A and it is an A, and if A is an A then it's not an A, you get into this endless circle. So the question is it or is it not A? Okay, so this is a very famous paradox. It actually took a while to actually originate, and here's the history of the paradox. It came about, I guess, in May 1901, while he was working on his real famous Russell and Whitehead book, Principia Mathematica. This was an effort to reduce all of mathematics to axiomatic set theory. And while he was doing this, he came across this inconsistency with membership in sets. Now there are some humorous versions of these, like the barber paradox. If you have a village where the barber only shaves people that don't shave themselves, who shaves the barber? And that's again one of these. If he shaves himself, then because he shaves himself, he doesn't shave himself. But if he doesn't shave himself, then he's one of the people that doesn't, so he shaves himself. So again, it's one of these circular reasoning that you find so often in paradoxes. Now, the importance of what is the practical importance of a paradox? The importance of a paradox is you expose the problems in your underlying system of logic. Now, there is a link to paradoxes right here under paradoxes, and this is just a link of what I gave here. Now there is sort of a relationship between paradoxes and unsolved problems and proofs and logic that we'll talk about in just a minute. But I wanted to go back to the continuation of the Greek mathematical system here. So Greeks were certainly very interested in philosophy for whatever historical reason, it's not clear, and this interest in philosophy led them to analyze very rigorously the ideas that they would use to answer mathematical questions. So Aristotle was very interested in the logic of proofs, and he came up with a system of logic and theorem proving and rational thought that was basically held pretty much intact until well past the Middle Ages, probably up into the 1800s. Similarly, Euclid's elements, which we'll talk about in a minute, were held pretty much intact and were used as a textbook up until the 1900s. So the Greeks also had some very famous problems, which are listed here and we'll talk about. One of the Greeks, well, Plato sort of epitomized this. He was very intrigued by the concept of an ideal, an abstract mathematical thought as an example of an ideal. For example, he came up with, or he would conceptualize the idea of a point and a line, a circle, and things like this. Now, one of the things he was very interested in, all of Greek society at that time was, what could you prove rigorously using only a straight edge and a circle? So everybody knows, for example, how you can bisect an angle by using a straight edge and a circle or a compass, basically. So the way that works, as you know, get another page here, is if you have an angle and you want to bisect the angle, you take a compass and you essentially draw a circle, so these two angles are equal. Then you take any other circle that of the similar, of a smaller radius like this, and then these 2 points here, and the line going through them will bisect the angle. So it doesn't look like it on this picture, but that's the idea. They can use a compass and a straight edge to answer geometrical problems. Now, it's clear that you can't necessarily answer every question, and in fact, one of the questions that they had, which was very famous, was the question of can you trisect an angle? Now, trisecting, they knew how to bisect an angle, and the question was, could you generate an angle by means of two lines intersecting, and then strictly with a compass and a straight edge, could you trisect the angle? And they could not do it, actually, and they tried, up until late on, in probably, the 1900s, they finally proved that it was impossible to trisect an angle with a straight edge and a compass. Okay? The Greeks obviously did not know this, because it turns out that trisecting an angle is equivalent to solving a cubic equation in integers, and that cannot always be done. Now, the Greeks knew that they could trisect certain angles, like they could trisect 90 degrees, right, because it came in to 30. But they obviously have a proof that you could not, proving that something was not constructible was not, they were not able to do that at that time. They had another problem, which was squaring the circle. That is, if you give a circle of radius, certain radius, say a unit circle, could you construct a square? Again, just using primitive geographical constructions of straight lines and compasses, or straight edges and compasses. Doubling the cube was another one of their famous problems. Could you take a cube of volume 1 and then construct a cube with volume 2 using, again, primitive geometrical constructions. All three of these are known not to have solution in terms of this. Now what I'm going to do is show you a way to construct a trisect an angle using a straight edge and a compass. We're going to argue that that's impossible. So what you're going to do is you're going to tell me what I've done that is not consistent with the assumptions of having a straight edge and a circle. So here's a method for trisecting an angle. This is really cute. There are probably more incorrect proofs. Now this is not incorrect, but it just doesn't quite fit the assumptions that the Greeks had. There are probably more incorrect proofs for trisecting angles than any other mathematical problem. And I'm going to try to dig up a couple and see if you can spot the errors in the proofs, because it'll be kind of a good way to analyze problem solving. Okay. So I'm going to have a circle of, say, unit radius, and I'm going to have an angle going from the origin, x here, to, so my angle is going to be this angle, phi is going to be the angle x, 0, e. Okay, so this is going to be unit radius. Okay, so what I'm going to do is I'm just going to take this and make this will be my straight edge. Right, and it's going to just have a unit radius here. Now what I'm going to do here, and this is possible, is I'm going to take this along here and I'm going to draw a line through that point. Oh, that was bad. See if I can delete that. Maybe I should just undo. Pause while I delete. Okay, now I've drawn it slightly better. But this, the idea is that this is a unit line here, and I'll get that just by moving the straight edge through this point, and so those two tick marks line up here. So obviously, since this is a unit radius here, and this is a unit radius circle, these two lines are the same. So I'm going to call this angle theta. So clearly, that angle is theta by the fact that you have two sides, and the angles opposite, similar sides are the same, etc. Okay, so this is equal to 1, that's equal to 1, this is theta, that is theta. Now the Greeks knew that the sum of the angles was equal to what? 180. So this angle has to be 180 minus 2 theta. Okay. Now, if that angle here is 180 minus 2 theta, guess what this angle is here? Must be 2 theta. Now, if this is unit radius, and this is unit radius, and this is 2 theta, then this is equal to what? 2 theta. Now, if that's 2 theta, and this is 2 theta, what's this angle here? 180 minus 4 theta, right? So that's 180 minus 4 theta. Now, if this is 180 minus 4 theta, this is what angle here? 180 minus 3 theta, and if that's 180 minus 3 theta, the complement is 3 theta. So if this is 3 theta, and theta is equal to the angle here, which I didn't write down here, but this angle here, you just trisected T. So the question is, A, is this wrong? If it's not, if it's wrong, tell me where. If it's not wrong, tell me why it's not a proof for trisecting the angle, because I just told you that it was impossible to trisect an angle with a straight edge and a compass. So, anybody, I mean, how many people think, I mean, look at this picture.
Wrong, but, well, look, you have 180 degrees in both triangles, right? And
right.
you're using 4 times one angle.
Right? I mean, you can look at this. If this is a unit length, and this is a unit length, these angles got to be the same. And if this theta equals that theta, this has to be 180. I mean, we know the angles do sum up to 180. That was available to the Greeks. So this is 180 minus 2 theta. So that line, it's got to be 2 theta. And it's, again, that line, this line is the same. So this is 2 theta. That's 2 theta. That has to be 4 theta. And this has to be 180 minus 4 theta. And if you add that theta, 180 minus 4 theta, you get 180 minus 3 theta. And the complement must be 3 theta. And if this is 3 theta and that's theta, that's 1/3. So the question is, what is going on here? Why isn't this a proof or a method for trisecting an angle? I mean, it obviously works. Well, in this case, the resolution, so we don't go around this all day. The fact is I've done something very subtle here, and I no longer have a straight edge. I have a ruler. Okay, and the Greeks did not say ruler and compass like most people say today. It was straight edge and compass. Now, straight edge has no markings on it, and if you don't allow markings, it's impossible really to construct this angle because you can't make a line segment with this equal to 1 unit length. But as soon as you make 2 markings on it, I mean, the Greeks knew how to bisect the line, and once you can bisect that, you have a ruler. And a ruler and a compass, this will show you a ruler and a compass, you can trisect an angle, but not with an unmarked ruler, that is a straight edge. Well, the thing is you're not allowed, see, the Greeks would say the Platonic ideal is a line, and a line has no intrinsic measure of length, so you're not allowed to add anything to this because the line has to be one-dimensional, and you can't make a ruler out of a one-dimensional line, like you have to put a vertical, like how do you identify it, right? So
you can't do it with a straight edge.
You cannot do it with an unmarked straight edge. You can do it as soon as you allow a mark of any length. I mean, that just becomes your unit length. You say, okay, just take your compass and make a mark on the straight edge and then use that to do it. And that'll work, but you're just not allowed to turn the straight edge into a ruler. That's the problem. So again, you have to make sure. It was very confusing for a long time. I mean, let's see, I have a reference here. Let's go actually look at the reference here on trisecting an angle here.
And what you did there, was that attempted proof that the Greeks did?
No, the Greeks would not have done that since it would not. They knew not to turn. They knew that they weren't talking about rulers. So they were talking about Platonic ideals of abstract geometry, namely a line with nothing, only a one-dimensional line and a circle. They had no thickness and things like that. Yeah, they had measurements of length. I think cubits and stuff were around, and stadia was one. They certainly, when they had the Olympics, they had. Well, they could have generated a ruler, but again, the ruler was not an ideal. The ruler was a realization of man of an ideal, and they were concerned only with abstract construction, totally primitive, if you will, in the sense of being an ideal construction. Let's see, if they have, I think they have a reference at the end of this as to when they actually proved that it was not possible to trisect an angle. It wasn't known in Gauss's day. Let's see. Okay, yeah. The proof of the impossibility had to wait for mathematics of the 19th century, and the final pieces of the argument were put together by Pierre Lancel. And he considered a general problem of deciding whether a geometrical problem can be solved with ruler and compass. And in 1845, basically, I guess he resolved it. So it had to wait essentially 2,500 years to do this. Now, there's actually another problem that, let me not jump ahead. These were three, I'd say these were the analog of Hilbert's 23 problems. These were the big three problems that Greeks for hundreds of years would try to do. How to construct a circle with the same area as a square, and doubling the cube. And part of the problem is that these are really related to the irrational numbers, constructing irrational numbers, and finite sequences of steps from rationals, which is obviously hard to do. And plus, the Greeks really did not have a good concept of the irrational numbers. And, of course, solving polynomial equations of high order and things like that. Their algebraic skills were not up to the geometry at this point in time. So again, this is an example of squaring the circle. You'll remember that we actually talked a little bit about the Babylonian problem, where you could take, say, a penny, you could take an 8x8 arrangement of pennies and very roughly make a circle of radius 9. And that actually gave rise to the Egyptian concept for pi as being 4 times 8 squared over 9 squared. So I'll let you go through and read through these problems here. There's another unsolved problem that dates back to Euclid, and under the link Unsolved Problems, we can do that. The third one here, it says, does there exist an odd perfect number? Now, the Pythagoreans were very, very geometrical. So, for example, and we actually have this concept even down to this age. So the idea of a square number is a number that can be put in like pebbles as the shape of a square. And this is how, of course, we do it today. 1, 4, 9, etc., n squared. We also have the triangular numbers. So they would have 1, and they would have 2 here, 1, 2, 3, etc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is 6, 3. So these were a series of triangular numbers. And the Greeks knew about squares and triangular numbers, etc. And Euclid posed, well, they also knew about perfect numbers. Perfect numbers were even more special because they knew about, a perfect number is the sum of its divisors, of the proper divisor. So, for example, 6 is a perfect number. So 6 is the sum of 1 plus 2 plus 3, and 1, 2, and 3 are all the divisors of 6. So the question Euclid posed, and it's in fact an open question today, 3,000 years later, is does there exist an odd perfect number? Okay? This is not they don't know the answer to this. Okay? As far as I know. Now this is again one of these typifies the kind of algebraic number theory type of problem of that time. They knew about square numbers, triangular numbers, perfect numbers, and they just asked all of the perfect numbers, they looked at a list of them and said, well, they all seem to be even. Does there exist an odd perfect number? Well, no one knows, and that means no one has come up with a proof that there is not, nor has one come up with an example of one there is. So here's one. Don't choose this for your thesis problem, but there's some old problems that really date back from a long time. Another example is the Goldbach's conjecture. And let me open that up in its own window here. This is actually one that had a prize of $1 million associated with it that just expired in March of 2002. So time's up, guys. So I have a link to it in Wolfram's site. Now, the original conjecture in 1742 in the letter of Goldbach to Euler states that every integer greater than 5 is the sum of 3 primes. Or we earlier rephrased it, it said that all positive even numbers greater than 4 can be expressed as the sum of 2 primes. Now, Faber and Faber offered a $1 million prize to anybody who could prove Goldbach's conjecture between March of 2000 and 2002, but the prize went unclaimed and the conjecture remains open. Now, various people did this by exhaustion. They looked at all the numbers up to 10,000 and said, aha, just by example, they wrote them as a sum of 2 primes. And then Bipping in 1938 extended it to 10,000 or 100,000, I guess. Then 10 to the 8th, 10 to the 10th. So right now it states it's all the way up to 4 times 10 to the 14th. All the even numbers up to that number can be expressed as the sum of 2 primes. So the question is, well, if induction were ever true by just giving a finite sequence of examples, this would certainly do it. It's true for the first umpty-ump billion trillion. It sure seems like it ought to be true, right? But unfortunately, that's not a proof, as we know. Now, there's another form called the Wheat-Goldbach conjecture that says that all odd numbers bigger than 9 are the sum of 3 odd primes. Now, there is a somewhat fascinating result here. It said that there was an upper bound on the number of prime numbers. So Vinograd said that every sufficiently large odd number is a sum of 3 primes. And Eastman, 38, proves that almost all even numbers, that is the set of measure 0 or not. And I think they said somewhere in here, I can't find it now, that you can show that all numbers are, here it is. In 1939, they proved that every even number can be written as the sum of not more than 300,000 primes. Okay? So that means that every even number can be written as a finite sum of primes, right, where that number is less than 300,000. But that's a long way from showing it's true for 2. But it gives an upper bound on the number of primes. So again, this is one of these fascinating puzzles that people have been hitting with heavy artillery for many years, and there was a $1 million prize. There's another fascinating one called let me open this again, called the twin prime conjecture. Now the Greeks knew about this kind of way of looking at mathematics because they would often pose a problem. People would work on it feverishly for generations in the various schools, and they would come up with a conjecture. They knew essentially standards of rigor and proofs, what constituted a proof or what didn't. They did not accept, well, I guess proof by construction they did. I mean, if you could actually construct a trisection of an angle by straight edge and compass, that would have been a proof to them. The twin prime conjecture says that there are an infinite number of pairs of primes differing by 2. So, see if I state that correctly. So twin primes, if you click on that one, that's just the primes that differ by 2. So 3, 5, 5, 7, 11, 13, 17, 19, 41, 43, etc. So if you look at tables of primes, some of them differ just by 2. The question is, are there an infinite number of combinations of primes that differ by 2? Again, as far as I know, that is an unsolved problem. That's an open problem. Now, we'll try to wrap this up here in just a minute. A closely related topic to this is proofs, and I'll assemble, along with paradoxes, lists of paradoxes, lists of unsolved problems that we'll assemble over the term. And in a future homework assignment, it will be for you to go out there and gather up paradoxes, incorrect proofs, unsolved problems, etc., and sort of analyze them. This is kind of a humorous article that you actually see a version of this on a T-shirt up in the 6th floor for the math. So these are, again, this is humorous, these are quote proofs and quote proofs. So there's proof by example, that's incorrect. Proof by intimidation, that's trivial. Proof by vigorous hand waving, parenthetically, works well in classroom or seminar. Proof by cumbersome notation, no one can ever understand what you're doing. Proof by exhaustion, so just give a proof that takes several thousand pages long. Proof by omission, and this is done an awful lot, where you have the ellipses, the 3 dots, or you have a sequence of things. You have to be real careful what you leave out, because if you leave out the right stuff, you can make an incorrect proof. Proof by obfuscation, it's confusing things. So just make a long series of statements that just totally distract the reader and then just hide something in there. Proof by wishful citation. Proof by funding. Gosh, I've got 3 different grants. How could it not be? How could it not be correct? Proof by eminent authority. I saw Carp, famous mathematician, in the elevator, and he said it was probably NP complete. Proof by personal communication. Just, say something that no one else could possibly verify. Proof by reducing it to the wrong problem. You take some unsolved problem, say that it can be reduced to a solvable problem, solve that, and then say that you solved the problem. Proof by reference to inaccessible literature. I remind you these are humorous, because we're not supposed to do this. Slovenian Philological Society, 1883. Proof by importance. Well, if it was true, there would be a whole lot of useful consequences, therefore, it must be true. Proof by accumulated evidence. There are no counterexamples. Proof by cosmology. If this were not true, the consequences would be unmanageable or meaningless. Proof by mutual reference. A follows from B, B follows from C, etc. Proof by meta-proof. Proof by picture. That's often done by students. Proof by vehement assertion. Just yelling at the top of your voice to make it true. Proof by ghost reference. Proof by forward reference. Proof by semantic shift. Proof by appeal to intuition. A couple of actual techniques that they miss are just by proof by assuming it's true. A lot of incorrect proofs are incorrect precisely because they somehow assume the conclusion that you're trying to get. And obviously, if you're trying to prove that A implies B and you assume B is true, or not, if you're trying to prove A implies B and you assume somewhere that something is equivalent to A implying B, then obviously you're assuming something that's equivalent to what you're trying to prove, and then it's easy to prove that from that way. You just go long enough and you just come back to your assumption in a different format and you've proved it. There's another somewhat humorous link to the most common undergraduate errors. I was thinking of posting some of this on a website because these are really fascinating. Okay. And also, for those of you who are not locally, I'm putting together lectures, and today will be the third and, lecture number 2 will be on Greek mathematics. Okay. Now, as requested, I will try to get on web a survey form that just asks you for some information about topics you're interested in the course and things you want to do, while the course is sort of rapidly coming to a kind of a closure as far as what I want to cover. I will try to add in more topics on the left here, so I would always check the news because the news will give you, again, important information as to when something new comes in. And don't always assume that all of these are static. Some of these may change. This course will be, at least from next lecture on, where we'll begin with Boas and Geller next lecture, Chapter 8. One thing I'd like to do next lecture is just talk a little bit about the techniques mathematicians have used to prove things. In other words, there are certain well-defined, and most of you know these instinctively, for using techniques of induction. And where proofs go wrong is where you inappropriately apply induction or incorrectly apply induction. So what I'd like to do over the course is to collect a page of incorrect proofs where the goal is to look at the proof and determine where the incorrect statement has been made. Because if you can spot an incorrect proof, that sharpens up your ability to look through logic and analytic reasoning to your own arguments. Because later on in the course, I'll be asking you for essentially rigorous demonstrations, proofs, if you will, of statements. So we're going to talk a little bit about how that works. Now, these are not going to be hard, I mean, in the sense of they're not going to be graduate level mathematics. These are going to be elementary mathematics, but you're going to look at solving these elementary mathematical problems in a way that is precise and rigorous. So again, in the readings, in the unsolved problems, I think the unsolved problems will be nice because by the end of the course we should have lots and lots of a broad range of unsolved problems. Some problems cannot be solved because they're intrinsically unsolvable. Some problems are just not solved because no one knows how to solve them, like Goldbach's conjecture. Okay, so next lecture we'll go to the 646 notes that you've all duplicated or have duplicated. And chapter 8 will be where we start. Come on, chapter 8. And what is that? That page what? Let's see. And that has to be after game theory. So. Yep, I almost got it. 72. Okay, set theory and foundations. Okay. I went too far. Okay, we'll start at set theory and foundations because this actually will tie into the paradox on axiomatic or foundational set theory that we talked about. We'll talk a little bit about the mathematical attempts to reduce all of mathematics essentially to an axiomatic system. We'll jump forward a little bit in time to chapter 13, which is Gödel's incompleteness theorem. You can read ahead on that, chapter 13. This is all not in next lecture, but we'll talk a little about the role of set theory and how you can formulate problems in set theory and how you would determine whether problems are solvable or not solvable, or statements are true or not true. So we'll go over a quick review, and I'll try to make since it'll be more than I can do in class, I'll make a list of mathematical methods that have historically been found, like reductio ad absurdum, laws of excluded middle, things like this. There are some classical mathematical techniques that have been used, or logical techniques. Some of these date all the way back to the Greeks and Aristotle. So we're going to talk a little bit about the structure of proofs, examples going back to the Greeks, and some current types of problems having to do with set theory. And everyone's had set theory, so it's not like it's going to be extremely complicated to phrase the question. Okay. Go through some of the references on the Greeks. A lot of them are very fascinating. Periodically, if I do add paradoxes, unsolvable problems, or incorrect proofs to the news, check that because some of them will be humorous. Also, I will post the first homework assignment later on today. It'll be on the web, so go and look. It will probably be under a link right here called homework. It's not there yet. But it'll have to do with the Egyptians, Babylonians, and the Greeks. So they'll involve a little bit of reading, a little bit of writing on your part, and a little bit of reasoning and descriptive verbiage that you can generate. Okay, so that'll probably be the only historical homework assignment. The rest will be more classical problem solving.